At the heart of the solar nebula, matter was crowding together, pressured by gravity and compressed into an ever-denser core. Over millions of years, the gas and dust surrounding this core spun and heated, forming a protostar, the early sun. It was a dynamic, turbulent object, still gathering mass from its surroundings while radiating faintly into space. As the core density increased, the temperature rose above 10 million Kelvin, hot enough to initiate nuclear fusion. Hydrogen atoms collided at extreme speeds, fusing into helium and releasing enormous amounts of energy. This process marked the true birth of the sun, the moment it transitioned from a collapsing cloud of gas into a self-sustaining star. Before reaching this stage, the protostar underwent a critical balancing act. Gravity constantly tried to crush it inward, while the energy produced by nuclear fusion pushed outward. When these forces reached equilibrium, the sun entered what astronomers call the main sequence, the long stable phase of a star's life that our sun still occupies today. The ignition of the sun had immediate effects on the surrounding solar nebula. Its intense radiation and solar winds began clearing away gas and dust, particularly from the inner regions. This clearing defined the architecture of the solar system, preventing the innermost planets from accumulating massive amounts of hydrogen and helium, which is why Earth, Venus, Mercury, and Mars are rocky, rather than gas giants. Meanwhile, in the outer disk, gas and dust remained cooler and denser, allowing the formation of larger cores, capable of capturing thick envelopes of hydrogen and helium, the gas giants Jupiter and Saturn, and the icy Uranus and Neptune. The sun's emergence thus set the stage for the division between inner terrestrial planets and outer giants, a key feature of our planetary system. The sun's birth was also marked by turbulence and magnetic activity. Twisting magnetic fields funneled material into high-speed jets that erupted from the star's poles, carrying away angular momentum and shaping the disk. This magnetic activity regulated how fast the sun spun and influenced the trajectories of nearby planetesimals. Observations of young stars in our galaxy, called T-Tauri stars, give astronomers a window into what our sun's infancy might have looked like. These stars are surrounded by disks of gas and dust, eject strong stellar winds, and are highly variable in brightness. They provide evidence that star formation is rarely calm, instead it is energetic, chaotic, and dramatic, with disks, jets, and collisions dominating the environment. As the sun stabilized, its light began to warm the disk, changing the chemistry of the material around it. Volatile molecules like water, ammonia, and methane could only survive beyond a certain distance from the star, known as the frost line. This boundary would determine the composition of planets and small bodies. Inside it, worlds would be rocky, and outside it, icy cores could grow and capture gas. Within a few million years of the sun's ignition, the solar nebula had transformed. The central star was fully active, the inner disk was clearing, and the building blocks of planets, dust, ice, and gas, were colliding and sticking together. Tiny grains were aggregating into pebbles, pebbles into planetesimals, and planetesimals into planetary embryos, setting the stage for a chaotic era of collisions and growth that would eventually create Earth. The sun's birth was not merely the illumination of a dark nebula, it was the ignition of a system, a cosmic furnace that would determine the structure, chemistry, and fate of all the planets forming around it. Without this star's steady light, the planets could not exist. Without its heat and winds, the planets could not take shape. In the next chapter, we follow the transformation of microscopic dust into planetesimals, the first true solid bodies in the solar system, the seeds from which Earth would emerge. In the swirling disk around the newborn sun, the solar nebula was a chaotic environment of gas, dust, and ice. Tiny grains, no larger than smoke particles, drifted through this spinning disk. Though microscopic, These grains held the building blocks of everything that would later become planets, moons, and asteroids. The first step toward creating worlds was their transformation from dust into larger, cohesive bodies, a process that might seem simple, but is filled with complexity and cosmic drama. These grains collided gently at first. Static electricity caused them to stick together, forming clumps slightly larger than themselves. Over time, these clumps grew into pebbles, still only millimeters or centimeters across. Gravity at this stage played only a minor role. The aggregation relied primarily on the physics of collisions and adhesion, where sticky surfaces allowed particles to cling together. As the pebbles grew, turbulence in the gas disk began to shape their movement. Some pebbles spiraled inward toward the sun, while others remained in the outer regions, where ice could survive. The composition of these early aggregates depended heavily on their location. For example, rocky minerals predominated in the inner disk, whereas in the outer disk, beyond the frost line, icy compounds became abundant. This variation would later determine the chemical nature of the inner terrestrial planets versus the outer gas and ice giants. When these pebbles reached sizes of tens to hundreds of meters, gravity began to take over. They collided and merged into larger bodies called planetesimals, the first true solid objects in the solar system, capable of exerting noticeable gravitational influence. Each planetesimal was a miniature world in itself, often irregularly shaped, and heavily cratered from continuous collisions. The process was far from orderly. The disk was a crowded place, with thousands of planetesimals interacting simultaneously. Collisions could result in sticking, fragmentation, or even vaporization depending on speed and angle. This chaotic dance of matter would continue for tens of millions of years, gradually building larger planetary embryos, from hundreds to even thousands of kilometers in size. The growth of planetesimals is supported by both theoretical modeling and observation. Young star systems observed with powerful radio telescope revealed disks with dense clumps and rings, a strong evidence of dust particles colliding and aggregating. While meteorites, millimeter-sized spheres called chondrules, primitive stony meteorite and chondrites, provide further evidence in our own solar system. These tiny spheres are direct relics of the processes that formed planetesimals and eventually, planets. Meanwhile, the Sun's gravitational influence and radiation pressure shaped the orbits of these growing bodies. Some were shepherded into resonance with emerging giant planets, while others were ejected from the system entirely. This sculpting ensured that the solar system would gradually form stable regions where planets could coalesce. By the end of this stage, the disk contained hundreds of planetesimals, ranging from a few kilometers to hundreds of kilometers across. These objects were the seeds from which the planets would eventually grow. In the inner disk, rocky planetesimals collided and merged to form the embryos of Mercury, Venus, Earth, and Mars. In the outer disk, icy planetesimals combined to create cores massive enough to capture surrounding hydrogen and helium, giving rise to Jupiter and Saturn. The journey from dust to planetesimal was a crucial chapter in Earth's story. It marked the transition from a diffuse cloud of matter into discrete and interacting solid bodies, the first tangible steps toward creating a habitable world. Without this phase, Earth would never have taken shape. There would be no collisions, no accretion, and no planet to hold oceans or cradle life. In the inner regions of the Solar Nebula, a violent dance of matter was underway. Hundreds of planetesimals, ranging from a few kilometers to hundreds of kilometers across, moved through the dense protoplanetary disk. Each collision carried enormous energy, fragmenting some bodies while merging others. This was the chaotic forge in which Earth itself was beginning to take shape. Gravity was the invisible sculptor. The largest planetesimals, slightly more massive than their neighbors, began to dominate local regions. Their gravitational pull accelerated the accretion process, drawing in smaller bodies and forming planetary embryos, protoplanets ranging from a few hundred to over 1,000 kilometers in diameter. Over millions of years, these embryos collided repeatedly, sometimes violently, releasing tremendous heat and melting their interiors. Proto-Earth emerged from this chaos, growing steadily through runaway accretion. Unlike the calm notion of planets forming smoothly, the early Earth experienced a tumultuous existence. Every collision added mass, momentum, and energy, raising the planet's internal temperature. The kinetic energy from impacts was converted into heat, creating a magma ocean, a molten layer enveloping the growing planet. This layer allowed heavy elements like iron and nickel to sink toward the core, while lighter silicates floated upward to form the mantle. The process was stochastic. No two protoplanets grew in exactly the same way. Some were completely destroyed in high-energy impacts, their remnants joining the building blocks of neighboring embryos. Others survived and merged, sometimes in head-on collisions, sometimes in glancing blows that sent fragments spinning into orbit. These interactions determined the final mass, composition, and angular momentum of emerging planets. One of the most critical aspects of this phase was the differentiation of the young Earth. The planet's interior began to separate into layers, a dense metallic core formed at the center, a silicate mantle above it, and a primitive crust on top. This separation was vital for the later development of the planet's magnetic field, tectonics, and ultimately, a stable surface environment. Without it, Earth could not have retained an atmosphere or oceans. Throughout this chaotic era, Earth was bombarded not only by planetesimals from its immediate vicinity but also by objects scattered from the outer disk. Some of these impacts were catastrophic, vaporizing portions of the crust and delivering volatile compounds like water, carbon, and nitrogen, essential ingredients for the future biosphere. The very building of Earth, therefore, was also the seeding of life's potential. This stage of planetary formation lasted tens of millions of years. Each collision, each merger, was a step toward creating a world capable of sustaining complex chemistry, and eventually, life. The proto-Earth was far from serene as it was molten, pocked with craters, and constantly reshaped by impacts. Yet it was during this time that the planet acquired its basic structure and began to evolve into a stable world. Among the most dramatic of these collisions would be a final, massive impact with a Mars-sized body, which would shape the Earth-Moon system and define the planet's early rotation. But before that moment, Earth continued its chaotic growth, absorbing planetesimals and planetary embryos, and accumulating both mass and energy. This stage, though violent, was crucial. Without the collisions, differentiation, and delivery of volatiles, Earth would never have been ready to host oceans, an atmosphere, or life. The story of our planet is, at its core, a story of fire, chaos, and relentless cosmic construction. Roughly 4.5 billion years ago, the young Earth was still a molten chaotic world, growing through collisions with planetesimals and planetary embryos. Among these countless impacts, one would be extraordinary, a collision so powerful that it reshaped the Earth forever and gave birth to its only natural satellite, the Moon. This is the giant impact hypothesis, the leading scientific explanation for the Moon's formation. According to this hypothesis, a Mars-sized body, often called Theia, collided with proto-Earth at an oblique angle. The impact released an unimaginable amount of energy, vaporizing large portions of both planets' crusts and sending debris into orbit around Earth. Some of this debris consisted of molten rock, some of vaporized silicates, all swirling together in a fiery, expanding ring. Gravity began to act on this debris, pulling it together to form a single stable body, the Moon. Unlike a captured asteroid or a body formed independently in orbit, the Moon's composition closely matches the Earth's mantle, supporting the idea that it originated from our planet's outer layers. Isotopic analyses of lunar rocks, returned by Apollo missions, reveal that the Moon's oxygen isotopes are nearly identical to Earth's, an evidence of a shared origin. The collision had profound consequences for Earth itself. The energy of the impact melted much of the proto-Earth's crust, deepening the magma ocean that already covered the planet. It also imparted angular momentum, giving the planet a faster rotation and creating the 24-hour day we are familiar with today. Over millions of years, the Moon's gravitational influence would slow Earth's rotation and stabilize its axial tilt, producing the relatively stable seasons critical for life's eventual evolution. This event also contributed to the volatile inventory of the Earth-Moon system. Some water and other light elements may have been delivered or redistributed during the impact, affecting the early atmosphere and oceans. The debris ejected into orbit formed a temporary disk, some of which reaccreted onto Earth as small moonlets, further stirring the molten crust. The Moon itself remained partially molten for millions of years, gradually differentiating into a core, mantle, and crust. Its formation marked a transition from a chaotic system of colliding embryos to a more stable planetary configuration. The Earth-Moon pair became a coupled system, their interactions shaping tides, day length, and orbital dynamics that continue to this day. The giant impact hypothesis is supported by several lines of evidence: the Moon's relatively small iron core, the similarity of isotopic compositions between Earth and Moon rocks, and computer simulations demonstrating that such a collision could produce a moon of the correct mass and orbit. While alternative hypotheses exist, such as multiple smaller impacts or fission from a rapidly spinning Earth, the giant impact model remains the most widely accepted explanation. This violent birth set the stage for the next chapters in Earth's evolution: the slow cooling of its surface, the differentiation of its interior, and the eventual formation of oceans and atmosphere. The Earth had survived chaos, collisions, and fire to emerge stronger, with a companion moon that would stabilize its environment and influence the evolution of life billions of years later. The story of the Moon's creation is a reminder that planetary formation is not a gentle process. It is violent, unpredictable, and awe-inspiring, a cosmic forge that molds worlds through destruction as much as through construction.